Okay, welcome back everyone to the second sessions of this first day of summer school. As I told you this morning, this first day will be a really full immersion in reinforcement learning. It is my pleasure to introduce Bo Dai. Bo is a senior research scientist at Google Brain in Mountain View. He obtained his PhD from computational science and engineering at Georgia Tech under the supervision of Le Song. Bodai is currently very active in the machine learning community as he is co-author of many publications in the major machine learning conferences. In the past 2 years, he also has been a guest lecturer and invited speaker in many different universities, conferences, and research centers, such as the SIAM Conference on Optimization, Facebook AI Research, DeepMind, and the University of California, LA. His research interests comprise learning to design algorithms, large-scale non-parametric machine learning, and reinforcement learning. We are really excited to have Bodai as a main speaker at this summer school, and we are very much looking forward to his lectures on reinforcement learning methods. In particular, he will focus on offline reinforcement learning and reinforcement learning with exploration. Many thanks, Dr. Dai, and the floor is yours.
Thank you. Thanks, Mathilde. It's my pleasure to give a talk here. Yeah, I'm Bo. I'm from Google Brain in Mountain View, and actually here right now it's 5 a.m. So you can think I'm just have a. You can consider I'm just have a very jet lag. Okay, so today I will give a brief talk about part 3 and part 4 of this mini course, which is offline reinforcement learning and optimization-based reinforcement learning and exploration. Actually, the similarity of these two parts is that all of these two, the content in all of the two parties most related to optimization. So we will see that how optimization can play a very important role for design reinforcement learning and help us to have better algorithm. So because this is, I know this is a control related emphasizes audience. So if you have any questions, just interrupt me, and I'm very happy to answer the questions. You know, this is a 4-hour courses, so it's a long time. So don't hesitate. Don't worry. Okay, let's see. The first part I will talk about offline reinforcement learning, and actually here you will have we propose a very coherent framework, and you will see literally how optimization can help us to handle reinforcement learning. So I don't know when I should read the slides. I don't know whether I should read this part, but because Niao told me this is a control conference, so I think it's better I have something here. It's like a very, very basic introduction about linear programming and Lagrangian dual. Roughly speaking, we call the can you see my mouse? Okay, great. Roughly speaking, we call this part as primal LP, which is because it's a minimal problem, which basically we minimize the object function, which is linear, and also the constraint itself is linear. And we always assume the solution exists, which means the problem is feasible. So that means it corresponding has a dual. And the dual problem corresponds to maximize some linear optimization with respect to a linear constraint. And you can see that actually this B corresponding to object function B prime, B transpose, and this A corresponding to this A. And the reason why we have such kind of optimization is that we can get it from the Lagrangian dual perspective. Roughly speaking, we have this Lagrangian as min-max optimization, which could be written in either this form and this form. And because we assume this primal form is always have a feasible solutions, that means AX bigger or equal to B always satisfied, which means consider you are trying to minimize something. This is negative, this part. And if y is smaller than 0, this part goes to, you see, infinite. So which means it cannot have any solution. So that means we need to restrict the y bigger or equal to 0. That's why we have this constraint in dual LP. And similar, if we return into this formulation, we know that x must be bigger than 0, and we are trying to sorry, we are trying to, let me see, maximize y. So which means we cannot have this component to be positive, this component to be positive. Otherwise, it goes to infinite. So we should make this component smaller than equal to 0, and which corresponds to A transpose Y bigger than C. So this is how we derive this two constraint in dual problem corresponding to LP, primal LP from Lagrangian perspective. Yeah, this is basic linear programming and Lagrangian dual. I think what I will, most of the case in this lecture, we'll just use this simple cases. So if you have any questions or have any, about this part, so you can write the questions down. Okay, great. I didn't see anything here. And let's pause here and come to a problem to say why we need offline reinforcement learning. Actually, Niao already introduced a lot of reinforcement learning, but in that style reinforcement learning, it have interaction between the agent and the environment, which means every time you train an agent, you need to use the agent to interact with the environment to get data from there by executing your current policy, and then collect the data to train your agent. And this is this loop is iterated, so on and so forth. We notice that this style of reinforcement learning actually have some limitation. For example, we notice, let's give a concrete example here. In the dialogue generation in chatbot, you want to train a chatbot, which means it will reply your questions or have a chit chat with a human. If you run this kind of, if you train such kind of thing interactively with human, you will see basically you need to hire a lot of people every day to interact with some agent which output randomly at the beginning, meaningless. So you see, this is insane, and it's hire a human could be very expensive in this case. And in another case, it's like a self-driving car. At the beginning, your driving policy can not guarantee there's maybe have some bugs. So if you just throw this kind of thing into the car and let it drive in the highway, you will see it's so dangerous to everyone. So basically, sometimes we really don't want to directly use our agent to interact with the true environment, because it's maybe unaffordable, expensive, or maybe cause undesirable disaster. So in such kind of scenario, the good thing that motivates us to propose this kind of offline reinforcement learning. Let's see what is concretely offline reinforcement. I think this above figure gives us a very concrete example and to distinguish the offline reinforcement learning to the online reinforcement learning. The first part actually is Euro reinforcement setting. You see, the agent every time is interact with the environment, and then collect the data to update itself. And this is iterate, so on and so forth. As I mentioned, this is sometimes impractical. So what we propose, called offline reinforcement learning, is that some agent which you trust collect the data for you, and the agent itself is only not interact with the environment. It is invisible to the environment, but only interact with this kind of logged interaction or collect the data. So that's what we call the offline reinforcement learning. I hope this gave you quite significant difference between these two kind of reinforcement style. If actually when I present this kind of stuff to many people previously, people will raise questions about how to distinguish the off-policy reinforcement to the offline reinforcement. So that's why I list the three figures here. Maybe you heard about offline reinforcement, and let's see how it's distinguished to the offline reinforcement. Actually, in offline reinforcement, we didn't prohibit the agent to interact with the environment. In another way to put it, actually it can interact with the environment to collect the data with your agent, with your current agent, and it will collect the data into a pool, which sometimes we call experience replay buffer, and so on and so forth. And the data collected in this pool maybe not just collected by current policy, it can collect by say like 1,000 step previously data, such kind of thing. So that means this buffer not just include the current policy, the data collected by current policy. It can also collect the data. It can also save the data, which collected by say like pi 0, pi 1, so on and so forth. And then you use this data buffer to train your policy. And this is called off policy because the data is not only collected by current policy. But you see, on the other hand, this is our offline reinforcement, which means there is some policy collected data, and your current policy, your policy to be trained cannot interact with the environment. It can only interact with the buffer collected by other policy. So this is the significant difference between the off policy and offline. Always remember, in offline reinforcement, you only have data. You don't have the chance to interact with the environment. So this is what we want to emphasize before we go through the technical detail and algorithm, how we solve this kind of problem. Okay, so I hope we are clear about the setting right now. Okay, great. Let's keep moving. Okay, so here's some here's some notation revisit. I think you already see the slides in Niao's lecture, and I just want to emphasize that we will still work on MDP. And you have, sorry, I noticed there's questions. I think it's better to interrupt me. Anyway, I will read it. So the question is like, if we update pi beta with the new pi in order to explore and drift to a better policy, it's not offline reinforcement anymore. Yes, that's true. Roughly speaking, in our previous slides, this pi b or pi beta actually is not visible to you. Let's give me another concrete example. For example, sometimes when you only have data, and sometimes the who collect data is not known to the learner. A very concrete example is like in recommendation system, there is a policy collecting data for you, and sometimes it's just a human or just a human rule such that encodes the prior knowledge about this kind of recommendation knowledge. And you never can explicitly written down the mathematical formulation for that. So this is one way to say you don't know the pi beta. Or even worse, sometimes in the scenario, you only have data. You even don't know who collected that for you. Another example is like in chatbot. What you observe is a bunch of the dialogue interaction, and you don't know who is interacting with who. You don't know which one is agent. It could be both human. Okay, so I think we are clear about this setting. Okay, another question is the difference between online and offline. Okay, So online is like it never have this replay buffer. Every time you current have your policy and you interact with the environment, you collect the data, and with this data collect from this pi k, you update your pi k to pi k plus 1, and after that, the data collected during this procedure is thrown away, and you do this iteratively again and again, update your policy. Remember, you never save the data. After you use the data to collect to update your policy, it is abandoned. And that's the significant difference between the on-policy or online reinforcement learning with the offline reinforcement learning. Okay, finally we will reach the notation side. I don't think I will read every notation here, but remember we keep the same focus on discounted infinite horizon setting. And yeah, this is the procedure of the MDP. Every time you have the state and you execute a policy, which A0 from some sample from a distribution, conditional distribution given as it will give the A0. And then the environment give you a reward R0 based on current state and action. And then your state will move to another next state by this state transition distribution. And this procedure iterates, so on and so forth. It could be goes to infinite long. And also, this slide is also very familiar with you. This is what I copied from Niao's slides. When Niao trying to solve the reinforcement learning, she just transferred the problem. Actually, the two core problem in reinforcement, one is called policy evaluation, the other one is policy optimization, to solving Bellman equation or Bellman optimality equation. Okay, that's a traditional way to solve reinforcement learning. Today, in this lecture, we will go through another way to view the reinforcement learning. It's not directly goes to the Bellman recursive equation, but look at this, what we call the policy value. Roughly speaking, it is expectation of the accumulated reward. So like this goes to infinite long, and you have R0, R1, and this gamma, as if you remember the notation, it is a scalar to do the discount. So this summation from T0 to infinite, gamma T RT, basically it's the cumulative reward for one trajectory. And this expectation is saying, because there are so many random things here, say like this initial distribution and the action and also random reward and random next state, so on and so forth. So there are so many random things here. So definitely one trajectory is not enough. We take expectation for that. And because this is executing this executing this pi by sample action from there, so we call this as the policy value. So then we can see that the policy evaluation is just trying to evaluate this quantity, and the policy optimization is trying to say, okay, I have this policy quantity. I want to find the policy pi such that maximize this quantity. That's what I wrote here. Let's see, this is two core problem, and in the setting of the offline reinforcement learning, as I mentioned, we don't have the environment, we only have data. Okay, the data is read as a lot of trajectory from I to M, and each one is the trajectory from S0 goes to S. It goes to infinite, but the S prime R is random variable from the distribution, and A is executed by a behavior policy. And I would like to emphasize that, as I mentioned, in some scenario, we don't know who collect data for you. So in that setting, we call it, we don't know pi 0, so we call it behavior agnostic offline reinforcement learning. And in this scenario, the offline policy evaluation will be, say, like, give the data set, and you want to find an estimator we had, such that it can approximate based on this data and also the knowledge of your policy. You want to make this quantity as a good approximator for the policy value, which is defined in previous slide here. Okay. And so the policy optimization is, as I mentioned, say like you want to justify the maximal policy, which we call optimal policy. Okay, actually, I want to emphasize why it is difficult, because look at the difficulty actually comes from you cannot access to the environment but only the data. If you say you want to do the policy evaluation and you can access the environment, actually this estimating this quantity is like a Monte Carlo approximation, right? You execute this policy along the MDP and collect the trajectory and do say like n times sample and do average, you will get a quite good approximation for this one. But this is offline reinforcement learning. So you don't know who collected data for you, and you have no access to the environment. So that kind of idea is not executable here. It's not applicable. So that's basically the major difficulty in offline reinforcement learning. And beyond these two core problem in reinforcement learning, actually there's some other kind of side problem, which is like offline imitation learning. It's imitation learning. It seems like you don't want to do any thing related to reward, but there is an expert behavior policy, and you just want to make sure you learn a policy such that the behavior of your policy matches the expert. So this is what we call imitation learning in offline setting. So same, you don't access to the environment but only data, but you still want to finish this task. That's what we call the offline imitation learning. And sometimes you don't want, as you notice here in policy evaluation, it's only a number, right? And you know, as the definition there's so many random things. So in some cases, only a expectation value is not enough. So sometimes we want to estimate a confidence interval for this quantity. So that's what we call the policy confidence interval estimation. And in this setting, we call it offline. Yeah, I noticed yeah, please go ahead.
Yes, so I had one question. So the reward function, is that you assume that this is known or you only have sample access?
Yeah, I only have sample accesses to it. As I mentioned here, it's a distribution. It can sample from it, but I don't know the detailed number.
So the exact reward function is also not known? Huh?
Yes.
Okay. Thanks a lot.
No problem. Yeah. So you see there are so many problems, and in this talk, I think I will give a brief introduction to what we have done in past 2 years. We propose a framework which can solve all this problem in a quite consistent way. And I will use the policy evaluation as a building block and a case study to give a brief idea how this kind of thing derived, and also introduce the rest of them. So, okay, so if we don't have questions, we may move to next slides. Okay, great. So as I mentioned, in the offline setting, it is really difficult because you cannot execute the policy. So in literally 20 years ago, people think we can introduce the importance sampling to do it. Right, that's a good idea, because you see, you don't know sample from here, but you don't know sample from here. So what you do is you just reweight them and do the important Monte Carlo approximation. The duration of this one is quite straightforward, but actually there are two major problems. One is because it's restricted to a setting where you know the behavior policy, which means you know who sampled it, and this must be known. And also, this must be a probability policy. Otherwise, if this is deterministic, you see, this is not doable. Okay. And the second part is the most terrible part. Actually, the variance of this estimator this estimator actually increase exponentially with respect to the horizon. In another way, if h goes to like 100, you basically cannot trust your estimator because the variance is so huge. Okay, the reason why it is so huge, actually intuitively you can thinking this is multiplication, a sequence of product. Okay, and we written it as exponential summation log ratio. And if you assume this part is bounded, it directly gives the exponential h times c. So that's the quantity of the variance. So it will kill you right here. So people notice this kind of phenomenon, and there are several efforts trying to combat with this kind of difficulty. So for example, the doubly robust estimator, which is very known technique. I introduced some baseline to do variance reduction. Yeah, it's very popular and proposed by Miro Dudik and Nanjiang Li Hongli. But in worst cases, the curse of horizon, we call it curse of horizon, is still not eliminated. Okay, this is the vanilla method before what we propose. Are we clear about this classic method? Great. Okay, next, from this slide we will introduce what we propose. So before we dive into the detail, let me first define some quantity. Bear with me, it's not too many. Okay, what we are interested in actually is this quantity. It is expectation. And so we define a quantity known as stationary state action occupancy, which is, you can roughly understand this as you execute your policy on this MDP and you count every step, every t time step, you count the distribution along the margin distribution, and then you do a discounted average, and it gives the distribution. Roughly speaking, that's a stationary distribution when you execute this policy on this MDP. And if you run long enough, it will give you it will stop on some distribution. So that's stationary state action distribution. And if you know this quantity, you can represent the policy value by expectation with this distribution with respect to the reward function. It's only one step, and you don't need to accumulate anymore because accumulation is already done here. Okay, so this is what we noticed. It actually is very important in later our algorithm derivation. So we transfer from expectation of accumulation to expectation with respect to a single stationary distribution. Okay, now let's see what happened later. And okay, there's actually by definition of the stationary distribution, we can have a similar Bellman recursion here. Let me derive it for you. So we know this is the definition of the stationary data action distribution. And we do one step expanding. Okay, so it's from 0 to t equals to 1. Okay, and then we expand this part. Okay, we expand this part. It will gives you because this t equals to 1, so we say okay, t from 0 and give me next state. So this component will comes out, and that rest part will be t equals to 1. And remember, by our definition, this component will be stationary distribution. Okay, so it gives you this characteristic recursion about the stationary distribution. Okay, it's quite similar to the Bellman equation, but if you look at the Bellman equation here, you will see this is integrate out of the past, but in the Bellman equation, it's integrate of the future. So it's like You will see it's actually primordial to each other. You will see later. Okay, we are clear about these slides. Now we have our major component to derive the linear programming reformulation of policy value. So as I mentioned, we can have, if the D is the station distribution, which means if D satisfies this condition, we can represent the policy value as expectation of the expectation of reward with respect to this distribution. Okay, so when we solve this optimization, it gives us the policy value. Okay. Remember, as we introduced in the first slides, this is linear programming, and its maximal can be understood as dual LP. So we definitely have the primal LP part. Okay, this is the primal LP corresponding to this LP. You'll notice if you look in carefully, you notice something very, very familiar with everyone. So what's this? This is basically it's the Bellman equation. Okay, but slightly different here is I don't need to find a solution which is exactly equivalent. I just find something bigger than that. It's enough because the object function will push my Q to make sure Q equals to the right hand side. You see, the object function is minimized. So it's pushed this thing to the smallest Q value to satisfy this condition. So that will say Q equals to this right hand side. So you see, indeed, this Bellman equation and the recursion relationship to this station distribution is primordial to each other. Okay, now we have our basic tool for solving this offline policy evaluation from here. Definitely you can not directly solve this optimization because 2 points. First one, this expectation is with respect to distribution of the current policy. You don't have data for it. That's one reason. And second one, actually, is this is for arbitrary state action. There are too many constraints. Say like if your state is continuous, which is very common, and this constraints infinite many. So you definitely cannot solve it. So how we deal with that? Actually, we introduced the Lagrangian part. Okay, by Lagrangian, you eventually represent the constraint into expectation part, this part. Okay, but still, there's one more step because this is expectation with respect to the on-policy sample, because this D, we don't have any sample from there. Remember, so we only have the offline sample. But don't worry, actually IPS gives us a very good idea, which is use important sampling. So we use important sampling, but we don't use important sampling with respect to the policy itself. We use important sampling with respect to the station distribution. Okay, this DD is the, basically you can think this part is offline data. Okay, and this is what we want. And then with this kind of stuff, we have this object function. You see, from here to here, I just do a important sampling. I've replaced this D to this DD, but introduce the reweighting part. Now we have every component, every expectation is approximatable by current data set. And so from here, I can use stochastic gradient or stochastic approximate, stochastic average approximation to solve this kind of optimization and get the solution. Okay, I noticed the questions. What is zeta? Or maybe you can raise the question directly because I need to switch.
Sure. Yeah, I wanted to ask exactly what is this zeta because I didn't understand.
Yeah, the zeta is like the in important sampling. If you sample from a base distribution, but you want to approximate to another distribution, you need to do a reweighting, right? That is my zeta, which is the distribution ratio.
Okay, is it chosen by the user?
Sorry?
So is it chosen by the user?
Oh, I see your point. Actually, it will be optimized this part. There's a typo. It's not maximize D anymore. It's maximize the zeta.
Ah, okay. I see. Okay. Right. Thanks.
No problem. So we call, actually based on this relationship, we developed several methods which we all name as sum dice. We call it dice family because it's short for the stationary distribution correction estimator. Okay. For this paper, it is original. It's derived first dice, but actually it's not deriving this way. If you look at this paper, it's very tedious. The derivation is so, although eventually you came this formulation, but the derivation is so complicated, you will miss somewhere. And later, this one generalized the method to the discounted, from discounted to undiscounted method. And finally, this paper actually is for, eventually we understand from the linear programming, it's much easier. So that's how we eventually come out this framework. Okay. Oh, I forgot to mention something here. In this formulation, actually, there are, as I mentioned, the first thing is it's applicable by SGD based on current data set. And also another benefit is that it's naturally compatible with the neural network because you can parameterize the, sorry, it's not D anymore, it's zeta and Q by any neural network you prefer. Okay, it's not changing the estimator. It's naturally incorporated because it's optimized. You just do max min with respect to the parameter of the neural network. That's good enough. And another benefit, actually, although it's not very significant, but you will see later it's very important in some application, which is you are estimating the ratio. While a lot of methods focus on estimating the Q function. Actually, the ratio itself is independent with respect to the reward function, which means you can, this method naturally applicable to the sparse reward MDP. But the Q-based estimation, for example, LSTDQ, which is very famous before DICE, is backing up the reward. And let's give a very extreme cases. You only have one state, which is 1, and the other state are all 0. Basically, it's not doable in the Q-based function because it's the reward is too sparse. Every location is 0, almost, right? So, but that's not a problem in here because for example, in this relationship, there's never corresponding to the reward. Reward only eventually comes out when you use this estimated ratio to do policy evaluation. So in your backup, actually in your estimating of the D or ratio here, you don't need to worry about the reward is sparse or dense. It doesn't matter. You will see an application later when this is important. Okay, so I think I mainly finished the major component of the dice, but we will see something here. Anyway, before I go to here, any questions?
So I would have a question actually. So in this box that is actually now on the second box on this slide, right? So you have the expectation on the second line, right? So this is the second expectation. This is with respect to the transition kernel, which you don't know. So will this expectation, so you assume that you can kind of approximate this expectation with.
I get your point. Remember, we have a sample like S, A, S prime, A prime from here. Yes. This part is never changed, right? If I sample from here, this is data, and then maybe I should go back to what the data looks like. Okay, here. Right, the data is given you as, you can thinking as 0, A0, and also S1, A1, S2, A2, and so on and so forth. Okay, you basically have the average, like, you can think this is cutting to tuple, say like S, A, R, S prime. Okay, so you have sample from S prime. Now come back to the estimator here. Although I wrote it into expectation, but you have sample as a reward function, as a reward S prime. And this A prime is from your policy, trying to estimate it. So you have another A prime from your target policy. So roughly speaking, this is linear, so you can extract this part outside, and every expectation can be approximated by samples. So that's a benefit. That's what I mean. Each term is approximatable by data. Okay, great.
And that's why, so that's basically the punchline why you don't need to know the transition kernel, right?
Exactly. I don't need to know. I don't even need to interact. I don't need to even sample from it because I have already a lot of data from there.
Thank you.
Okay. So we have 10 more minutes. I hope I can finish the first component. Okay, so actually, we, based on that kind of basic knowledge, we introduced several components for regularizing. For example, this component, it's regularize the Q function. Okay, because this is statistic. So we know from statistical machine learning theory, when you just do the unregularized, it's not good enough. So we need to introduce some regularizer here. So this is regularized for the Q function. This is regularized for the ratio. Okay, and we even notice that because, as I mentioned, D is not depends on R. So sometimes you can eliminate it. Say set alpha R to 0. It doesn't matter actually. You will see this from this table later. And also this lambda is we're trying to emphasize that, trying to enforce the ratio to be a valid ratio, which means the expectation D, sorry, the expectation DD with respect to the ratio equals to 1. So if you incorporate such kind of constraint by the Lagrangian, it will automatically have this lambda here, although I didn't mention in the derivation. So this is how we have this kind of regularized here. And from this table, we carefully profile every combination of different setting of this for regularizer. When we bold it as unbiased, which basically it's not unbiased because space is not enough. Actually, it is asymptotic consistent, which means if I have infinite amount of data, the solution will be unbiased. So but the biased part is not. We mainly focus on the unbiased part. Biased part is not good enough. So, which means even you have the regularizer, you still can choose some setting in some combination in this table to make sure your solution is good enough. I mean, unbiased, asymptotic unbiased. And we also notice that after you obtain the Q and obtain the ratio, there are several ways to do the policy estimator. One is we call it dual estimator, which is at the beginning we just do reweighted expectation with respect to reward. Another one is like a vanilla thing. You do the expectation with the Q function. And because these two are all unbiased, you can combine the two together. And also remember the Lagrangian itself is unbiased estimator. The Lagrangian itself, after you solve it, actually the solution itself is equals to the solution to primal and dual. So it is another estimator. So that's how this three estimator comes out here. Are we clear about this part? Okay, so you can find this table and how we derive it in this paper. It's not showing here, but you will see in the reference. Okay. Yeah, here.
Sorry, might I ask a question?
Sure.
On So the first question is, what exactly is this F1 and F2 functions?
F1, F2 are just two convex function. Roughly speaking, for example, the L2 norm is a good example. It's convex, so that's we sometimes use for regularizing. It's not, some norm is not large.
And the second question would be like on the previous slide you had for the Lagrangian, the first expectation was with respect to S0 and A0. So why is that exactly? Because before it's not with, it's with respect to.
I see. Let's see how we derive that. So actually it's come from here. Okay. When you're in the Lagrangian, you time this one with Q function here and Q function here, right? So you see this component will automatically give you that you need to take expectation with respect to the initial state.
Okay.
Okay.
But then in the regularized version, it's. Yeah,
regularized version is not. It's not. Actually, it doesn't matter. Actually, to be honest, not that matter. But we didn't regularize it with respect to initial. We regularize it to a whole collected data.
Okay. Thank you.
Okay. Good. So here, I don't want to go to this one. This is saying with this understanding, we can formulate a lot of existing methods by setting different by different regularized combination. And actually, this is what we proposed, and this is proposed by Nanjiang and his student. And this is very famous LSTDQ proposal, which is actually a standard state-of-the-art method before our method. And this is what we empirically found performs the best, which we call the best dice. Okay, I think that's how this slides. What's this slide trying to say? Now, let's see the real performance. Actually, we have more experiments in the paper, but let's just look at this simple case, which is richer in the Mojuko study. Mojuko is the current benchmark for reinforcement learning. So we want to do a policy evaluation. And this Richard is saying like the policies control this arm, and eventually you want to have this green dot end of this arm to reach the target. And as I mentioned, it's offline. So we compose the policy like this. This pi b is some policy. And this pi is what we want, the target policy, which we want to estimate the policy, which we want to estimate its value. So the alpha is like you tell how much is similar to your target policy. So here is alpha 0, alpha from small to bigger. So it makes this sampling policy becomes more and more similar to your target policy. Okay, we compare our method with some TD method, and also important sampling, which is basically in IPS method, as I mentioned before. And this red dot line is the true value. As you can see, when we increase the number of samples, the proposed method, actually, no matter alpha from 0 to alpha becomes alpha bigger, which means the policy is the behavior policy is become more and more similar to the target policy. The method performs, our method performs very close eventually to the true value, but the other one basically failed. It's just because the variance is too large. You cannot control it in this case. Okay, this is empirical study. Okay, now I think I'm on time to finish my first component. Yeah, any questions? Good. Okay, then in next session, I will discuss a little bit about the property of this dice family, especially answer the questions whether it still border from the curse of dimension or not. And also, I will introduce how this method could be applied, how this method could be applied to a real problem, which is have the sparse reward. Actually, Mathilde, I was wondering, I'm not sure. Should we stop
Yes.
here, or we can keep going and eventually have a 20 minutes pause?
As you prefer, we could either have a shorter pause now or continue and have a longer pause later.
I don't know how the students think which one's better. I'm fine. Fine with it.
Generally, they like more shorter pauses, but it's yeah.
Okay, then we can stop here. Yeah.
Then okay, then let's make a pause now and reconvene in 10 minutes. Okay.
Yeah, great.
Okay, great. So let's see each other at 3.
Sure, sounds good. Let's.
Awesome.
Okay, so since we don't have any questions about my major algorithmic part, let's go to the major questions we want to answer. Whether this method breaks the curse of horizon or not. Actually, that means besides the empirical super performance compared to the IPS method, theoretically, whether we solve the curse of horizon problem. In another way to put it is whether the variance of the certainty, whether the variance of the estimator is polynomial with respect to the horizon. And actually, the answer is yes, and it's even better. Let's look at this theory. And the theorem, if the total, if the total reward is bounded. Actually, here's a little bit subtle. If you just think the reward function is bounded, then eventually the bound will depend on the horizon. Okay, but in another way to put it, if we say the value of the policy is bounded, it means it's independent of h. Then we can cancel 1h from the results. So let's assume just the value function or value itself is bounded independent of h, which is very common in practice. That's what we call total bounded rewards. And another assumption is a little bit, actually it's something what we are doing right now, but let me explain that to you. Another assumption is called data coverage, which means for every state action pair. I know this is a little bit restricted, but anyway, for any state and action pairs, you need to make sure it is visited at once. It is visited. So in another way to put it is at least your data covers all the support of your distribution of state and action pairs. So we prove the theory in a tabular case, but I think in our paper we extend this one to the linear mixture MDP. But anyway, let's come back to the tabular case. So in this case, under this two assumption, we can show that the estimator, which is denoted as V hat, compared to true value, actually, eventually, absolute value is in the ratio, in the rate of 1 over square root of KDM. So K is the number of episodes. In this case, for simplicity, we didn't consider the infinite horizon. We only consider the finite horizon. But I think there's a relationship between the finite horizon and the discounted MDP by changing factor of the horizon h to 1 over 1 minus gamma. But anyway, let's in this particular setting, it's fixed finite horizon with h, and then you can see this bound. It's not depends on h. it's a little bit weird, but if we throw away the assumption, say it's the total reward bounded, it's gone, but you only bound the reward, and then there will be a h in front of this. There will be a h here. So, but anyway, in either case, we say it's not exponential with respect to h, it's polynomial. So in this case, you can trust the estimator or not? No. Okay, this is the theoretical part of showing that indeed our estimator is it's better compared to the IPS. Okay, next we will have several slides trying to introduce how we prove this kind of stuff. I mean, proof sketch, but make sure the high level idea is carefully bound the variance, and also utilize the recursion structure in the v function, in the value function, when you bound this kind of policy value here. And and what I want to emphasize is that this algorithm also achieves the lower bound of our policy evaluation. And this is quite new result in our paper on archive. In there, we both proved we have detail for this theory and also the lower bound proof. In this talk, I will not talk about how to prove the lower bound, but only this upper bound proof here. Let's start. First of all, we prove, actually this is known to many people, but we formally say that in this tabular case, the algorithm from the dice family actually is equivalent to a plugin model-based estimator, but it's only valid for the tabular case. So that gives us benefits that we can estimate the plugin estimator instead of complicated optimization. Okay. Here, in another way to put it is we have a closed form of the solution. So we don't need to worry about optimization anymore. And then another important lemma is that value difference lemma. So which means I give you a policy and the true value of your policy compared to minus the estimated value by this plugin estimator could be written in this formulation. Here, C hat actually is the station distribution estimator. In other words, compared to my previous slides, it could be understood as D hat. And this I hat is estimator of the reward function, and this P hat is estimate of the conditional distribution or transition distribution based on the data. And the proof of this one actually is quite simple but tedious. How we get here is by definition of this V and definition of the V hat and expand it and also use recursion. I think I will not introduce how we exactly get here, but remember this is some important lemma we want to from. Based on this lemma, we change the original object function to this part, and then we can bound each term in this thing and eventually get the solution. That's the basic idea. Okay, how? Let's see the first component, which is very simple. It's one step. You don't need to consider this VH thing. It's just one step. So in here, we call it error from the reward estimation. And it's easy. We utilize the Bernstein inequality. Okay, before I proceed, do I need to introduce the Bernstein inequality? Okay, fine. I just briefly introduce it. It's like a probability inequality which trying to distinguish the estimation of your expectation from data and true value with respect to the finite number of your samples. Roughly speaking, that's called. There are so many such kind of probability inequality, but we utilize Bernstein inequality here to get this bound. Okay, this is one component, and the difficult part actually came from the second part. Second part actually is super tedious. We denote this part as delta 1. we throw this away. So this component is delta 1. This is what we call total variance. And we try to bound this term. If you just simply apply the probability in constant here, you will not get the optimal dependence to H. It's just because this is summation to H. So if you simply bound this term, definitely there's some H here, right? So that's not good enough. And remember, so that's why we go to another strategy, which we first rewrite this using a Cauchy-Schwarz inequality. So we have this term, variance term. And then we apply the Bernstein. So we eventually get this part. And now what we need to do next is we bound this term instead of here. The reason we bound this term instead of here is because we have some recursion for this v function, for this variance function. So that's the magic thing here. We didn't use, so remember, we didn't do here. We changed to a upper bound of this quantity. The reason we can bound this upper bound with some quantity optimal with respect to the H is because we utilize its recursion again in the variance bound. Yeah, I know this is tedious. Actually, it is tedious when we prove it. So you can see here, we denote V1 equals to this one. You see, this is exactly the thing here. Okay, and then if we I equals to say 0, it is exactly this term. Okay, but we want V1 0, but we notice there's a recursion relationship like this. V1 I smaller equal to square root of some constant here, and V1 I plus 1. So that's what we call the recursion structure in the variance term. And with respect to this constant recursion, we can solve this recursion and eventually gives you V1 0 is in this order. Okay, I know this is tedious, and before I move to next slide, any questions about this part? Okay, it seems like silence, but I really want to emphasize that if you want to achieve the optimal dependence with respect to H, you cannot simply from here. You cannot do that. You need to utilize still Markov recursion structure in your variance term, and eventually it gives you what you want. Okay, and from with with this and plug back into the original term, you eventually get the delta smaller than square root of KD. This eta actually is some log term. Actually, you can basically throw away and becomes O tilde or square root of KD plus 1 over KDM. Okay, so we have this term bounded and also previous term bounded. Now we have this two component, and this combine these two results, we get what we want, and we finish the proof. Yeah, I know this is tedious, and I want to give you a brief introduction, a brief sketch of the proof. So, any questions about the sketch, proof sketch? Okay, so then let's move to a real application of our method. in this application, we really want to do a policy evaluation, dialogue evaluation, which means you want to evaluate some agent, which really solve a problem. Let's make a very concrete example here. The agent itself is having it's an air ticket booking agent. Basically, it's interact with the customer, and the customer is trying to communicate with this agent to book a ticket. And then during this conversation, you can see the agent express his intent, and the customer expressed its intent, and the agent looking to the database to eventually fulfill this order. And if this task is completed, we say the reward is 1 because it's successful booked. And if it's not, we set this reward is 0. And you see this is indeed a sparse reward, because during this whole procedure, there's no reward assigned. Eventually give a 1. Okay, you can think during this whole procedure until you reach here, it's all 0. And particularly concretely in this setting, we formulate into MDP first. And basically that means we want to match action state and transition. Action state transition from here for this particular application. Let's see what's it. What's wrong with my laptop? Okay, so in this particular application, we said action A is just the agent response, and the state is the conversation history. And as I mentioned, the reward is just the finished task or not. It's very sparse. And the transition is given current conversation history and the feedback from the agent. The human will have some reaction. Okay, this gives you the basic component of the MDP. And by this construction, we reformulate the dialogue evaluation to policy evaluation. Okay, great. So we are clear about the problem setting and how this one is transformed to the policy evaluation problem. Okay, so let's see why it's difficult. As I mentioned, in this setting, the reward is super sparse. And because you only obtain the reward at the end of the dialogue. During the whole procedure, you'll never have any guidance. And another difficulty actually is because the conversation actually have varying horizon, finite horizon, which means you cannot directly use the dice or whatever algorithm for infinite horizon MDP, because in this setting, you don't know where it ends, when it ends. It maybe ends in 3 or 5 conversation or even longer. So the data set is quite different. And also another quite difficult part is that the state action space is computationally large, because we have humans have very large vocabulary size. And each sentence is combinatory from this state, combinatorily picking from the vocabulary to compose the sentence. And then in our setting, the state is the history of the whole conversation. So you'll see it's combinatory. So eventually, actually, the state space is already large enough, right? And the action is composed sentence is also large, which means in this setting, no matter how many data are collected, it seems impossible to satisfy the data coverage assumption in our theory and method derivation. So this is 3 major difficulty in applying the policy evaluation to evaluate dialogue. So, okay, so let's see how we beat each of them one by one. First of all is that, as I mentioned, that's estimator is independent with respect to reward. You don't need to worry about the sparse reward anymore, because when you're estimating the density ratio, it's independent with respect to reward. And the reward eventually only used for compose with the ratio to get the policy value. So it doesn't matter to estimating the ratio. But the Q-based method, for example, LCTDQ, which is the state of the art before, is highly sensitive to this setting. Okay. And the second one, we say the conversation is finite horizon. Don't worry, we propose some method to do that. Basically, we call it pseudo state padding. We will see what's that later, very soon. And when we want to handle the competent large state, we introduce some function approximator. Basically, Robota is a language model. I'm not sure because I know this is a control-based community, so you guys know about language model, right? Okay, I will have several sentences to explain what it is. You may be heard about a lot recently about BERT or GPT-3 or so on and so forth. This model trying to, you can thinking that this model is like first to extract a feature representation of the sentence, and then use this feature representation to predict next words to generate the whole sentence for sentence generation. In here, we use one model, one particular language model, but we throw with the language generation part. We just use the feature extract from this model as our function approximation part. I hope my explanation is clear to you guys. Or in another way to put it, just neural network extract the good feature. Is this clear? Good. I think this is quite some side words. I think this part, this language model is recently very exciting progress of machine learning for NLP. And if you are interested, you can read a little bit about this one. Okay, so let's see one by one how we deal with it. First, we'll discuss about the pseudo state padding. Okay, this, as I mentioned, in this application, we really don't know how long it is. For each conversation, the T could be varying a lot. So for example, in this case, it's finished after this big T step. And then we said, okay, we will not stop here. We will add more pseudo state from T+1 goes to eventually T max. Okay, so by this padding, we eventually make sure every conversation eventually have the same length, but it's still finite. And then we say after we reach this T max, we sample from we goes to beginning and sample from the initial distribution and do it again. So this goes to iterate and many times. So basically, this one goes to infinite long. Okay, so by this pseudo state padding, we eventually get a augmented MDP. It's different from the original MDP because now in this augmented MDP, it is infinite horizon. Okay, and but then actually after this padding, the very natural question is that whether this padding is valid, which means after this padding, whether our dice is applicable. That's one question. Another one is whether this value or policy value on this augmented MDP still can generate original. Let me rephrase the sentence. I'm a little bit sleepy. Whether the original policy value on the varying horizon MDP can be recovered from your execute the policy valuation on this augmented MDP. That's the second question. Actually, we provide the confirmative answer to both of them. First one, we prove that you can see this definitely this augmented MDP is not ergodic because it's periodic. this is cycling, right? But even that will show that there's a unique stationary state action distribution, which means we can utilize the dice estimation now. The proof of this part actually is quite simple. We just find it in our paper. We just find it and verify it is the stationary distribution. And secondly, we show that the policy value in this augmented MDP is rescaling. Sorry, here's typo. It's not recalling, it's rescaling the original value by Tmax. So that means after you estimate the policy on this augmented MDP, you just divide the value with Tmax. That's good enough. That's the best. That's the original policy value in the original MDP. And then in the coding part, actually, we didn't do this padding. Oh, we didn't do this padding. This is only do it conceptually. Okay, so it's not introduce any actual computational cost. That's what I want to emphasize. Okay, I think this is pseudo-state padding. Because you guys don't know, quite familiar with language model, so I will not go to the detail here. Just remember, the language model is used here for feature extractor. You can think this part as a very, very large neural network to extract the feature from this state, this combinatory state action, which means the sentence. You use neural network from sentence to extract a feature, and this feature will say like, for example, either go to a linear model or go to neural network to eventually parameterize your zeta and the q function. So here's not v, it's the q function. That's, remember, in our dice. So in our dice, it's it goes too fast. In our dice, it's this two component, this zeta and the q function. And we utilize a very good feature so that you don't need to worry about you literally cover every state action. You are in the feature space right now. Okay, so let's see. We already finished the major technique to combat the difficulty in applying the outpolicy evaluation for this dialogue evaluation. Let's see how it performs. Okay, before we go to the real comparison, we just do ablation study to see the effect of sparse reward. And here we cover this method in gamma with we replug the LSTDQ, replace the dice. So you see, because it's sparse, the performance now is far away from the true value. And these are two agents, and the dollar is their true policy value. And this is what LSTDQ gets. And now here we use dice, and you can see the we converge to the true value very quickly. Okay, so that gives intuition. Also give a very straightforward illustration that this sparse reward indeed affect a lot in different algorithm. Okay, so next is a very boring table. You don't need to read the detailed number here, but remember, we compare to the state-of-art policy, dialogue evaluation method. And for this air ticket booking agent evaluation task. And this is correlation number. The larger the better. And you see our method achieve the state-of-the-art compared to model-based one. The cell play is model-based evaluation, which first evaluate a human. First, actually, here environment is a human, so you need to first model the human and execute your policy with respect to the human. So you see, that is not very good because human is very difficult, very complicated to model. So our method don't need to model the human. So it's achieve much better performance with respect to current state of the art. No matter Pearson correlation or Spearman rank correlation. Oh, here is another illustration. Say we we visualize the correlation between the solution and the true value. And this slope is 1, the closer to 1, the better. And also the data point here close to this horizontal 1 is the better. Oops. And compared to our method in the first row and the model-based one, you see the variance is very huge. And also this line is more close to the line with slope 1. So that means the dice family actually performs quite well compared to the model-based one. Okay, I think I just finished how we particularly apply this method to a very difficult real-world policy evaluation problem. Okay, we'll stop here and any questions?
Yeah, excuse me.
Yeah, sure.
Can you hear me? Yeah, it's okay.
Yeah, I can hear you.
I have a question about the data coverage, and especially when we have a policy that do not explore the environments very well. So meaning that we have states that are not covered. So when we evaluate a policy that is not the same policy as the behavior policy, so if this policy go towards states that are not visited, that means that our offline policy evaluation will give bad results, right?
Yes, yes. Yeah, that's actually the thing I'm trying to, I'm not trying to bypass, but trying to mitigate by utilize the language model to extract a feature. Actually, your worry is very valid. Actually, that's also our worry, concern at the beginning when we initiate this kind of project. We know what we collect the data is not sufficient enough. So there will definitely a lot of state and action, which here is a lot of conversation we never observed. So we utilize the language model to extract a feature such that as long as the feature is similar, we sort of have some ability to mitigate such kind of difficulty. But your worry is definitely valid. I would say even with this kind of language model to extract a feature, there's still some difficulty to generate some policy which is too far away, in the sense that their station ratio is too large. It's still very difficult. I totally agree with you. Yeah.
Okay. So when you use your offline policy evaluation to find out a new policy, you use some optimization process to find out?
No, actually here we only finish the policy evaluation, which means the policy is fixed. We're never trying to improve it. We never try to improve it. We just want to have, say like, give a quantitative score to each policy so that we can compare to which one's better. We never say we want to improve that policy along this offline data.
Okay, I got it. Thank you.
But actually, you raised very good questions. I will cover later, which is the offline policy optimization. Yeah. Any questions about this part? Okay, so then let's see next part. I think here, as I mentioned, we propose a very consistent, very unified framework to not only handle the offline policy evaluation, it also can be generalized for other kind of tasks with this kind of perspective, with this kind of optimization perspective. So in later this session, I will talk about how we can use that dice family do the offline policy optimization. And later, maybe in next session, I will also talk about how how this method could be applied to other tasks like offline imitation learning and offline confidence interval estimation. Yeah, I put offline confidence interval to last because it's quite difficult. Actually, we'll consider that problem for a while. But anyway, let's first focus on how we can utilize this method for offline policy optimization. Okay, actually, this kind of extension is not that difficult. Recall, the policy optimization task is that we want to eventually maximize the policy value, right? Now we already have good estimator for the policy value, as I mentioned, at the dice family, which is this term, right? If you still remember, this is Lagrangian form, and if you solve it, it just gave me the policy value. What do you need to do? Actually, it's quite straightforward. Maximize it, right? So this is intuition and also the idea to do it, but there's some difficulty if you just straightforward do such kind of stuff, because this is offline data, and you really don't want to say like direct optimize this one, because sometimes if your data is not good enough, for example, some support is not covered sufficiently, then what you optimize here actually will not trustable outside of the data domain. So we introduce something here. Oops. So we introduce regularizer here. This minus alpha expectation df zeta. This f actually is a convex function, as I mentioned. And let's proceed. And let's see what's this regular indeed trying to do. Okay, ignore this two box. Actually, this regularizer is equivalent to a F divergence between your stationary distribution and the data you collected. This is not too difficult to derive because this is a ratio. And let's see if this is negative log. And if this is ratio, so you plug the ratio d pi over dd here, and it is negative expectation dd with respect to log d pi over dd. So obvious, it is the KL divergent. So that this effect of the this regularizer is indeed trying to restrict your stationary distribution, not go far away from your stationary distribution. Actually, this is what we want, because as I mentioned, if your data is not very covered, it's not covered everywhere, you really don't want to go that far. And actually, this philosophy is not only applied here. Recently, there's a lot of batch reinforcement learning paper which just introduce a different regularizer, but still follow the same spirit. Constrain your policy, policy not go far away from your data. For example, the BAC and a lot of recent paper just trying to do this. Some paper use the KL divergence. Some paper use MMD, maximum mean discrepancy, and so on and so forth. But naturally, this can be very efficient, convenient to incorporate into this dice framework. So you just introduce this regularizer. You don't vary too much, and also maximize this pi. Okay, this is if you want to look into the detail, just refer to this paper. Okay, I think until now, I think I finished the object function for offline policy optimization. And let's look at the property of this object function. Actually, before we achieve the conclusion, I will make a claim that the gradient of this object function with respect to policy is a policy gradient. So in another way to put it is that even your data is not executed, it's not on policy, it's not executed by yourself. it's collected by other behavior policy. You optimize that object function. What you get is unbiased estimator for your policy gradient. Let's see how we achieve that. We take a gradient with respect to pi, and let's see where pi shows up. Actually, it shows up in this box and also in this box, because this A0 sample from pi, and this A prime is also sample from pi. And the rest of the component in this object function is independent with respect to current to pi. It depends on d and zeta, but it's independent of the pi. Okay. And after we solve the optimal for this max and the min, there's a theorem, or there's a lemma called Danskin lemma. So which means you don't need to worry about the dependence with the d and the q with respect to pi. You can treat it as the optimal part is independent with respect to this pi. So when you calculate the gradient, you only calculate the gradient for this two terms. The rest of the term is, you don't need to worry about that. Is this clear to anyone, to everyone? Okay, and then let's proceed step by step. And remember this zeta, after you solve it, actually it's d pi over dd, and then you plug this part into your expectation. This is what you get. Okay, so here's mu pi and here's d pi. And I reorder this term and extract the partial derivative outside of everything and recall this relationship. Eventually, what you get is like this. Okay, and here you can see I do one more step, log trick. Okay, I will introduce log trick later, but believe me, this is what eventually the gradient. Okay, I will introduce the log trick in the policy gradient family. It's in section 4. And here, believe me, this is eventually what you get. And we call it policy gradient. And it is indeed what we want. So this is quite interesting. You just use the offline data, but eventually you still get unbiased estimator for the policy gradient with respect to unpolicy sample.
So sorry, wouldn't this mean that we can do policy gradient, which typically is online, via instead offline data, so in an offline fashion? Yes,
exactly. But I hide something here.
Okay.
The thing I hide is you already noticed that in the proof condition, in the assumption of the theorem 1, which is saying I really need the data coverage. See, I can handle the distribution shift only by the mass shift. But if your data say like just restrict to some domain and the other domain is not observed, I can do nothing. I think this is not only restricted to this method. Actually, this is also the problem of the statistical machine learning. In the vanilla statistical machine learning, the best you can do is just predict over the support of a distribution, right? You can never do out of distribution prediction. But we do here we say by this important sampling, we can handle a little bit about the distribution shift, but still not go beyond the support.
Thanks.
Okay. Any questions about this part?
So basically, if I try to translate it again to understand, so the behavioral kind of data that you have, like this D to the script D, right? So this needs to visit all potential state action pairs.
That's true.
That's kind of a hidden assumption, and otherwise you could not say anything about the xi function there.
Exactly.
Sorry, the zeta.
Exactly.
Okay.
Exactly. So
Okay.
essential. This is about let's say in the important sampling. If your proposal is very bad, it not cover the whole support.
Mm-hmm.
Your estimation is very bad.
Mm-hmm.
So this is the thing. This is the problem of this important sampling. Okay, I think we are clear about this optimization part. Actually, here's some similar results for policy optimization. We still under the assumption that total value is bounded, not reward is bounded. I mean, total value is bounded, and also data coverage. We can still have the difference between your optimal policy value. I mean, the policy you obtain from data compared to that value with optimal value is still in this rate. It's similar rate. The high value is actually quite similar, and you just need one more step to decouple the error. And this is difference from here. And we introduce the stepstone. This is V hat, which means you estimate your optimal policy on the data. And compare this two components, definitely this one is smaller than this one. Otherwise, you will pick pi star instead of pi hat star. Okay, remember you are doing maximal policy evaluation, maximal policy optimization. So this term is smaller than 1. So these two terms are the left. And this first term, we call it error on fixed policy because it is policy evaluation of the true optimal one. So with theorem 1, we can bound it, right? Remember theorem 1, this is do a policy evaluation basically. But this term is actually, it's a little bit tedious. I don't want to look into detail, but remember why it's tedious. I just explain why it's tedious because both pi hat and v hat are dependent on your data. You need to carefully handle the dependence in this two terms. But here it's not because you see the policy is given. It's never related to your data. So it's just a policy evaluation, but here it's not. So we need some actual effort to make it eventually bounded by this term. But good thing is this term in terms of the sample is not the leading term. So it's a high order term. Don't worry about that. But it's have some dependence with the state. So anyway, it just looks like this. Yeah, I think this also gives you a illustration. This kind of method actually performs quite well in terms of the horizon. Definitely under the assumption, theoretically. And now let's see, we really do some empirical study to verify our method performs quite well. This one is the famous 4-room synthetic data. So this is starting point, and this is target point. This is I don't remember which. It's actually t from 0 to some number, but I don't remember its concrete number of t equals which one. But you can think this just we execute our algorithm iteratively again and again. We just pick 4 of them to give an illustration of the whole algorithm procedure. This arrows is say the policy, represents the policy. And this shadow part represents the Bellman arrow. So eventually, the Bellman you can think that this basically guides you which what's the optimal policy you get, and eventually you can see here that's quite a good policy already visually. And also, we definitely compare with some state-of-the-art model-free algorithm like soft actor critique and TD3 and DDPG on the module code. We just pick two examples here. One is called Walker 2D. The other one is humanoid. And the blue line is ours, and the rest line corresponds to our competitor. You can see the corresponding here. We don't say we beat all of them, but we are comparable with them. Yeah. So yeah, this is the empirical study. Okay. Any questions? I think still on time. Yeah. Any questions?
So I have a question, if nobody else has a question, which is like, where is the size of your state and action space entering your kind of error bound on the previous, like before your empirical study, you had like this kind of, approximation errors on the cost evaluation, right? So yeah. This DM, I guess, like this depends on the size of the state and action size pairs. So because I'm wondering, like later, if you can use like this method to do kind of a policy optimization, right? So I'm wondering where the curse of dimensionality will pop up. Yeah.
Good questions. Actually, in this setting, we didn't observe that. It's linear with respect to state and action. Okay. And if you say curse of dimension, we can think that the state is a discretization of say like RD. Mm-hmm. And this S will represent as exponential with respect to the curse of dimension. Okay. Because this is tabular, and here S represents number of state. Mm-hmm. So I think this term shows up. Yeah. But with careful analysis, average dependent, I think almost this is optimal. But I don't know whether this is optimal or not. But in terms of leading term, in our case, it's achieved the lower bound already. Yeah. Yeah.
Excuse me.
Sure.
I don't understand. How do you get your results with Mojoko and the empirical results? What kind of policy do you use for get your data?
Oh, for this one?
Yeah.
Good questions. Actually, in this paper, we're still executing the off policy thing. We still, but it's a little bit different. We say like we still, after we train for a while, we still use this one to collect the data and use that. You can think of this as our policy, but we didn't collect data that frequently. We describe the detail in our papers.
Okay.
If you want to ask particularly for current moment, people use what kind of behavior policy to collect data? I think, let me tell you, they just execute some algorithm for a while and then use that algorithm, freeze that algorithm, collect data, and use the data set to train the rest of the algorithm. This is particularly, I think there's a benchmark collected by Sergey Levin, and this is what they're doing.
Okay.
Any other questions? Okay, good. I think I will stop here.